took our time static gauge for x0 was equal to tau and generalized it for a linear combination of x's characterized by a vector n to be defined sometime later, a constant vector n, and we replace the x0 equals c tau condition by this one. We had introduced a alpha prime. Then n dot p, we said there was the momentum of the string. Any momentum of the string is an integral over the string of p mu tau and sigma, always over strings the momentum density, if the boundary conditions are such that all the components of p involved in this dot product are conserved. This is a number, and actually then we fix the parameterization of sigma in such a way that we make this density constant along the string. So not only this is n dot p is this, but n dot p mu, this p tau, is constant over the world. So this is a number. Then we show that n dot p sigma is equal to 0. Because n dot p sigma must be 0 at the end of the string if those things are supposed to be free. P sigma, remember, is the thing that has to do with the boundary. And then we looked at the formula for P sigma and derived that this must be true, which is a generalization of the condition of orthogonality between the sigma, the constant tau lines, and the constant sigma lines of the string. That's generalized. So we want to continue this and find a little more that these conditions imply. Let me alert you that this is for open strings, and we said that this pi was there because we wanted to parameterize the open strings from 0 to pi. In the case of closed strings, we always want to parameterize them from 0 to 2 pi, twice as long as an open string. It's very natural, 2 pi for periodicity. That's sort of the obvious thing. So for closed strings, I think there's no 2 here and there's a 2 over here. Please see the book if you need to use them, and you may need them at some time. So we have this condition, and now we consider the other aspects of this thing. So what happens to our p tau mu? Well, p tau mu is one of those objects that is fairly complicated, as you remember, 1 over 2 pi alpha prime, but it had 2 terms here, and one involved x dot x prime. But now that is 0, so that simplifies dramatically, and you get x prime squared times x dot mu over square root of minus x dot squared x prime squared. And this part you remember because that's a Nambu-Goto square root, and that Nambu-Goto square root has x dot x prime squared minus x dot squared x prime squared, and this part was 0. So this is as simple as it has gotten given this condition, which is nice. Now we want to dot this with n because we know all kinds of things about n dot p and see what this implies, and it certainly will tell us something interesting. N dot p tau would be 1 over 2 pi alpha prime x prime squared and dd tau of n dot x. So this is dd tau and n dot x. But n dot x is simple here, so we know what that dd tau is. We can substitute it. And we know what n dot p tau is as well. So the left-hand side, you use the second equation, and it's n dot p over pi, 2 pi alpha prime, x, I forgot the square root below, x prime, and dd tau of n dot x is 2 alpha prime n dot p. So, time to cancel things. N dot p goes away, the 2 alpha prime goes away, the pi goes away, all the numbers go away. And you are left with 1 is equal to x prime squared over square root of x dot squared x prime squared. As simple as that. This is this factor that actually was here. That factor is 1. Look, p tau mu has become very, very simple with this factor being 1. But let's unpack this by squaring it. So you get minus x dot squared, x prime squared is equal to x prime squared, x prime squared. X prime is non-zero because it's a space-like derivative on the string. The string always exists in space, so x prime squared is non-zero, so you can cancel 1 with 1, and we get this very nice equation. X dot squared plus x prime squared equals 0. Which together with this, did I give them numbers? Yes. 1 and 2. 1 and 2 give you the Virasoro conditions again in a slightly more covariant way. X dot plus minus x prime squared equals 0. That is by combining 1 and 2, adding twice 1, or subtracting twice equation 1 to this one, you get these complete squares, and these two things must be equal to 0. Remind you that the way this looked before was ddx dt plus 1, ddx is sigma plus 1 over c ddx dt squared equal 1. This is how our Virasoro constraints looked in the static gauge. Now they look a little more interesting, a little more covariant. If you use the static gauge, you will recover this thing again. So these are our conditions, and then what happens? P tau mu is now 1 over 2 pi alpha prime dx mu d tau. Very nice. And P sigma mu, well, if you have what we were writing last time, you will see that things again simplify quite dramatically. The only difference is really a minus sign, and this is x dot squared, and this is x prime. And this minus sign, because x dot is really minus x prime squared, ends up giving you the following, as you can imagine, dx mu d sigma. And with this, the equation of motion, which is dd tau of this plus dv sigma of this equal to 0, becomes EOM just x double dot minus x double prime equals 0 for any x. The wave equation.
Yeah, could you please on the microphone?
Oh,
Thank you.
sorry. You were hearing me well, though, I think. Just that it's not recorded. Okay. Okay, now it's better now. Okay, so our wave equation is there, everything is there, we can proceed. Now we're going to do, in the classical context, the steps that you will do in the quantum theory for the rest of this course. This is the notation that everybody that does quantum strings uses. But we arrive at it classically, and then in 2 lectures we'll say, oh, these are operators, these are not numbers anymore. And the notation is the same. So this is the key notation of the theory that we're going to use now to solve equations. As you will see, it's sort of pretty nice notation. The first impression may be funny, but let me do this. So we're going to solve for free open strings. So this time, P sigma mu must be 0 at sigma equals 0 and pi, but P sigma mu just means the x mu, the sigma will be 0 at 0 or pi will be 0. Now, what kind of functions satisfy this? Rather than doing the whole derivation, but it's relatively easy, you can really guess what is the general solution of this problem. So I'll guess it. These functions that satisfy this are cosine of n sigma, because their derivatives are sine of n sigma, and those vanish at 0 and pi. So we're going to get superpositions of cosines of n sigma. But you also need to solve the wave equation. So you need things that solve this thing. So this will be multiplied by things of the form e to the minus plus or minus I n tau. So this involves sines of n tau and cosines of n tau, and those satisfy this wave equation. If you take 2 derivatives with respect to tau and 2 derivatives with respect to sigma, they solve the wave equation. So how do we write this? Now, bear with me a little. What's the most general solution of this equation, wave equation? Well, there can be a constant. We'll call it x sub 0 mu, as opposed to capital X mu. It's the 0 mode of this x. Now, there can be a term linear in tau or a term linear in sigma. Both terms would satisfy the wave equation, because wave equation is 2 derivatives of tau, 2 derivatives of 0, so both satisfy. A term linear in sigma doesn't look like good news, because dv sigma would be non-zero, and that probably is just a terrible thing to put. Indeed, you cannot put it. So a term linear in sigma cannot exist. It can exist in some cases in closed strings, which is quite interesting, but not in open strings. So we'll put here a term linear in tau, and you will say, oh my God, what are you putting there? Yeah, I'll put this constant in here, square root of 2 alpha prime. I will put the alpha 0 in here, and I'll put the tau. The tau is going to be dimensionless, so this is supposed to have units of length. And this thing carries the units of length. Alpha prime have units of length squared. So remember, h bar equals c equals 1. So this alpha 0 is dimensionless. And it's a constant. And why would I put this coefficient here? Well, bear with me a second. Now we'll put the term that has to do with oscillations. And I'll put an I to alpha prime. Now, don't be worried if you think you wouldn't be able to invent this. This was invented after a lot of trial and error. So I'll put coefficients like that. Sum over n different from 0, alpha n mu e to the minus I n tau cosine of n sigma. Okay, this is what I'm going to write, and I want to justify it a little more. So far, this is a solution, and these terms solve the wave equation. The boundary conditions are fine. The sigma just comes from here. Sines of n sigma vanish. So boundary conditions are good. It's a solution. It's the most general solution. These are the most general functions over an interval 0 to pi that vanish at the endpoints. The derivatives vanish at the endpoints. And now two things that may look a little funny. The i's, the 1 over n's here. If this is a number, why didn't you just absorb it? Again, this is the units thing, so that probably makes sense. And here, there's one more thing that is very important. This thing should be real, and it doesn't look real. X is supposed to be real. What are all these imaginary numbers doing there? Well, this term must be real, and it can be guaranteed that this term is real if alpha n mu star is actually equal to alpha minus n mu, which we will assume. Because if we take alpha n star, and if you take the complex conjugate of this then will become a minus n. This will become like a minus n. This doesn't change, but cosine with minus n doesn't change. The n, well, everything is becoming minus n. So this actually, with the I, when you take the complex conjugate, it becomes like minus n. And please check it, but it's almost clear by inspection that this thing is real now. But you can check it. Just take the complex conjugate, and you will see the sums positives, the sums negative trade with each other, and it becomes the same. And this should be real. Yes?
Why is 1 over n?
For convenience, that you will learn in about 1 minute. And what is it that we're trying to do? What is the problem in here? What is the hard part of this game? Constraints. So this was designed extremely cleverly to simplify the constraints. So let me show you how. Well, first another thing. What is the physical interpretation of this constant? You usually think that a position is initial position plus velocity times times, or momentum divided by m over times time. So this must be related to the momentum of the string, this constant alpha 0. So I really need to know what it is. So I have that p tau mu, the momentum density, is 1 over 2 pi alpha prime dx d tau. Have it there. So I take dx d tau here, and what do I get? There's 2 alpha prime and 2 alpha prime cancel. Here we get 1 over, well, I'll write it, 2 pi alpha prime, square root of 2 alpha prime, alpha 0 mu, plus lots of terms that I don't want to bother to do, because to calculate the momentum of the string, I'm just supposed to integrate over sigma from 0 to pi of this p tau mu. Remember, momentum density, so let's integrate it. And when I integrate it, when I differentiate with respect to tau there, all these terms will have cosine of n sigma. Integrated over sigma will be sines, and from pi and 0 you get nothing. So these terms do not contribute to this integral. The only term that contributes is the one we have there, which is 1 over 2 pi alpha prime square root of 2 alpha prime, the alpha 0 mu, and the pi from the length of the string. Everything was a constant. So what do we get? the pi's go away, and there's a alpha 0 mu over square root of 2 alpha prime. So we've learned that alpha 0 mu is in fact 2 alpha prime times the momentum. So that letter alpha 0 mu is basically the momentum. And if you want to get your equations right, you better put that square root of 2 alpha prime there. So, any questions so far? Yes?
So why the 2 alpha prime?
Why did I put the alpha prime there?
The 2 alpha prime and the momentum?
Where?
So,
Here?
so the second term is tau is momentum. The second term of the solution is tau is the momentum, and it's 2 alpha prime.
No, I'm sorry, what is the question? I actually don't understand.
So if you plug in alpha 0,
Yeah.
we just got, then we get not just momentum times time, but we also get 2 alpha prime.
That's right. 2 alpha prime times momentum times time. So, so that must have the right units in normal units. So this is length squared, and momentum is mass, so it's 1 over length. And that's length, because tau has no units, and this has length.
And so the 2 is...
The 2 is, it's convenient. Not tremendously convenient, but convenient. Yeah. Okay, so now let's do these derivatives. We need to know x dot and x prime. So here comes the first one. How about x dot mu? What do we get? Let me do this term first. So if I differentiate with respect to time, I get minus in. The minus I and the I go to give you nothing. The n cancels. That's why the n was there. And therefore, I lose the I, lose the n, and I get the sum over n different from 0 of square root of 2 alpha prime alpha n mu e to the minus I n tau cosine of n sigma. Good. But now I missed the first term. For n equals 0, or this term is missing. I just differentiated that one. So I should get an extra term when I differentiate with respect to tau of 2 square root of 2 alpha prime times alpha 0. Square root of 2 alpha prime. And when n is equal to 0, well, that's nothing. And n equals 0, nothing. 1, 1, alpha 0. So actually, the only thing I need to do now is to say all n. And I even got the n equals 0 now. So that's pretty nice. That was well designed. How about x prime? X prime mu, again, let's try to differentiate just the second term. Now I have to differentiate the cosines. So it's going to give me an n that cancels that, a minus sign and sines. So minus I square root of 2 alpha prime, sum over n different from 0, alpha n mu e to the minus I n tau sine of n sigma. Okay, that's it. There's no 0 term here because there's no sigma. But, you know, life is easy now. If n is equal to 0, this vanishes. So might as well n over all integers again. That time, now it's all good. And now they look very similar. And that was also the reason we did these things like that. Because now I can combine x dot mu plus minus x prime mu. And what do I get? Well, I get square root of 2 alpha prime, sum over n belonging to the integers. And look, you have the same coefficient here, alpha e to the minus n. That is cosine n sigma minus I sine of n sigma. So it combines to an exponential. It's really well done, this thing. So what do we get? We get alpha n mu e to the minus I n tau plus minus sigma. Let's check the top sign. For the plus, you should get cosine n sigma and minus I sine n sigma, so it should be e to the minus I n sigma. And that's the right thing, e to the minus I n sigma. So that's it. This was the reason for everything pretty much in this formula, that the constraint is simple. The constraint is nice. Okay, let's see. Front goes up more, and middle goes up more. A little more, maybe. Front. Okay. So we're ready to do the live code. Question? Good? Right? So, light cone. So this time for light cone, we're going to choose the vector n to be 1, 1, actually over square root of 2, 1 over square root of 2, 0, 0, 0, 0, 0, everywhere else. So n dot x is equal to x0. Look, the n mu is with the index down, so you don't get an extra minus sign. You have n mu x mu. Remember, this is n first, x first, or n plus x plus n minus x minus. You sum over those indices. So these are in normal coordinates here. Actually, I'm sorry, maybe better. Let's do this like that. N0, x0, n1, x1. The sign arises when you raise or lower the index. So here, n dot x is x0 plus x1 over square root of 2. And that is what we called in our first lecture x plus. And n dot p would be p plus by complete analogy. So our gauge condition, the top thing boxed in red, has become x plus is equal to 2 alpha prime p plus tau. That's all we'll need to do. Now, strategy. What are we hoping for? What are we going to do in the light cone? The idea in the light cone is always the same. The plus components are given. The light cone gauge condition affects the plus components. Therefore, look, x plus, if you think about it, actually it's sort of pretty interesting here. X plus, and that connects to the question we had here. Look at x mu was equal to x0 mu plus 2 alpha prime p mu tau plus, because alpha 0 was that, And look, x plus is equal to 2 alpha prime p plus tau. So it's of the general form of this solution, but assumes that x0 plus is 0 and assumes that all the alpha n pluses are 0. That's our Lightcon gauge condition. So in terms of a general solution, the Lightcon gauge condition says that for x plus, when mu is equal to plus, only this term survives. And all these other things are 0. That's x plus. Now, we have some constraints. So what are we going to do? We're going to claim the following is true. If you know if xi's of tau and sigma, i's, these capital I's are indices that run over 2, 3, up to d. Remember, all the indices are plus, minus, and I. Capital I is used for everything. So if the xi's of tau and sigma are known, suppose you know the xi's of tau and sigma, or you state them arbitrarily. That is, you state all these x0 i's, the alpha 0 i's, the alpha n i's, you give them all. All the xi's are known. This can always be made into a solution because the constraints that are up there can be solved exactly, and the only thing they're going to do for you is determine x minus of tau and sigma. The whole motion of the string is determined by x plus of tau and sigma, which happens to be known, x minus of tau and sigma, and xi of tau and sigma. And the idea is that given the gauge and given that this is known, the constraints, the only thing we'll do is give us x minus. And that's it. We'll be all done. We will have a solution, a complete solution. So, how do the constraints look? Our constraints are x dot plus minus x prime squared is equal to 0. Remember, if you have an a dot a, that's minus 2a plus a minus plus a vector dot a vector, the vector component of a. Our Lightcon metric is minus for plus minus, minus for minus plus, and that's this. So this term is the following. This is x dot, x plus dot plus minus x plus prime times a minus 2 times x minus dot plus minus x minus prime. So the first vector with a plus, the second vector with a minus, at minus 2, plus the same thing but with I. So x dot I plus minus x prime, x I prime, times x dot I plus minus x prime, xi prime equals 0. Now, I want you to realize why Lightcon is so powerful. If you had worked this in conventional coordinates, Minkowski, this would be minus a0 squared plus this is the transverse vector from components 2, 3 to infinity, plus here would be plus a1 squared plus a2 squared plus all these things. Now suppose you knew this and you wanted to find a0, you would have to take a square root. And square root and quantization are not friends. It doesn't work so well. It's complicated. On the other hand, here is a product of different things. So if you want to solve for a minus, you just get this and no square root. And that's what's going to happen here. Now, something even more nice happens here. X plus has 0 prime derivative, no sigma. So this is 0. And x dot plus is just 2 alpha prime p plus. So this whole thing is minus 2 times 2 alpha prime p plus times this x dot minus plus minus x minus prime. So not only we were lucky that we can solve for this, but this whole thing has reduced to a number, plus the term that we have here. I just won't copy it. So we get our answer. And our answer so far is that x minus dot plus minus x minus prime is equal to 1 over 2 alpha prime, 1 over 2p plus, and I'll write it like this, x dot I plus minus x prime xi prime squared. You know, that's fairly clear what square means. It just means sum over those capital I's. So look, this has been very successful. This is an important equation. So from here, you can take sums and subtract. You can write the first equation, the second, add them and subtract it. So find x minus dot and x minus prime. This equation gives, not find, gives. And it's a simple calculation. It's just sum and subtract, and it's a simple formula. So if you know x minus dot and x minus prime, you actually can calculate x minus anywhere on this surface, on this world sheet. If you know, and let's think what x minus involves. If you know, let me say it this way. Here is the world sheet of the open string, and you have a point. And suppose you know x minus at this point, at one point on the world sheet. Then you want to know it here. Well, you take, say, the lines of constant tau, and you integrate x dot minus from here to here, and then you integrate x minus prime from here to here, and you find what x minus is here. So, in fact, dx minus is equal to dx minus d tau times d tau plus dx minus d sigma times d sigma, and this is x minus dot d tau that you know, plus x minus prime, the sigma that you know as well. So you can integrate dx minus anywhere you wish and find what its value takes anywhere. So it's just determined up to a constant of integration. And given the way we write this x's over here, x minus, a constant of integration will be called x0 minus. So this and the knowledge of x0 minus will determine x minus of tau and sigma completely, as we will see now. So, you know, this, I think the impression this should cause is that, yes, we have a solution, and it's a little somewhat interesting. The x minus is quadratic things on the transverse coordinates. But, you know, it seems like x minus is supposed to be some expansion, and I don't see the expansion yet. We're going to do it. And is there a complication for open strings or for closed strings? There's a small complication, possible complication for open closed strings. And the complication is the following. In an open string worldsheet, suppose you want to go from here to here. You integrate here and here. But then you could also integrate this way, or that way. And you will get the same thing because each pointer can be modified to each other. But if you have a closed string, and you want to go from point P to point Q, you could integrate this way, or you could integrate this way. And you may not get the same thing. So this integral is written in a funny way, and it seems that it always determines x minus, but there could be a problem for closed strings, that somehow you may need to prove that all ways of integrating give the same answer. In fact, you could even do the following. You could start on a closed string at a point P and integrate x minus and see if you get to the same value of x minus when you return. So you would have to check that integral from 0 to 2 pi d sigma of dx minus d sigma is equal to 0. Isn't that obvious? Because it's an integral of a total derivative? Not quite. It looks like it's an integral of a total derivative. It's not all that simple. You see, if you look at what x minus prime is, let's just get an idea. This is very funny, because you get from here x dot and x prime. And you say, OK, are they consistent? And you could say, well, let's take a sigma derivative of this and a tau derivative of that. They should give the same thing, because this d sigma, d tau, d sigma. But it won't be obvious that it happens. Actually, it will be the same if the equation of motion holds. Similarly, the x minus is obtained by taking this equation with a plus and subtracting the one with a minus. And when you subtract the one with a minus, you'll find that x minus prime is, roughly speaking, when you subtract this, you'll get the xi dots times the xi primes. So x minus prime is not obviously a sigma derivative. It is a sigma derivative if you use equations of motion and you verify that things work correctly. But the way x prime comes out is not d sigma of something. It comes out as something that is not a d sigma. Therefore, this constraint is very non-trivial. And you will find in one exercise that how you deal with it. It's the beginning of what makes closed strings somewhat more subtle and more complicated than open strings. Open strings, you have all these boundary conditions. It looks like a mess. And it's very rich, the d-branes and all that. But closed strings, this periodicity and these non-trivial closed curves that you get make topology and other things very, very interesting. So, OK, let's solve front those. OK, so let's do the following. I'm going to try to use that equation there. So the claim is that xi of tau and sigma, p plus and x0 minus, determined x minus of tau and sigma completely, which roughly was shown here, but not very explicitly. We can say we can integrate it and get it. But now let's just get it, at least for the open string. So what do we get here? Well, I'm I need those x dot i's plus x primes, xi dots plus minus xi primes. I need them. But I know what they are, because they're all of this form. So I just put an I, and I get square root of 2 alpha prime, sum over n, alpha n I, e to the minus I n tau plus minus sigma. Good. That's not so bad. Now, how about x minus? We want to figure out what x minus is. So, x minus of tau and sigma, given our general expansion. X minus is just another coordinate that needs to be solved. So, I will write it. It's x0 minus plus square root of 2 alpha prime alpha 0 minus tau plus I square root of 2 alpha prime sum over n different from 0, 1 over n alpha n minus, the index is always a minus up, e to the minus I n tau cosine of n sigma. So indeed, I know x0 minus, I assume I know it. And somehow knowing x minus means that you're going to find what alpha 0 minus is and what alpha n minus is. If you know those things, you know what x minus is. Now, this same formula also holds for x minus, so we can write more compactly here that x minus dot plus minus x minus prime is equal to 2 alpha prime sum from all n alpha n minus e to the minus I n tau plus minus sigma. All right, so this thing is equal to that right-hand side. So what is that right-hand side? That right-hand side is 1 over 2 alpha prime over there. 1 over 2p plus, and now I have this xi plus xi prime squared. So I have the square of this thing. So the square of that thing, the 2 alpha prime square roots go this, and now I have two sums. Sums over p and q belonging to the integers. For the first factor, I would put e to the alpha p I. For the second factor, an alpha q I. And then e to the minus I and p plus q here, p plus q, tau plus minus sigma. I multiply these two sums, and please look at them for a second until you're convinced that I did it right. I was doing that top equation in the blackboard there, this leftmost top equation, and I squared that thing using this thing and two indices p and q. And look what has happened that should make you very happy is that you have a sum of exponentials and a sum of the same exponentials. So this can be used to find alpha n. In fact, I'll go all the way up to here. This is the 2 alpha primes cancel, 1 over 2p plus. And what I'll do here is I'll call p plus q, I'll call it n. And I will sum, instead of summing over p and q, I will sum over n and p. So change the labels of the sum. So you will have the sum over all n. And then the sum over all p belonging to z. And what do we have? alpha p, q now must be put n minus p. Alpha n minus p I. And then I have e to the minus I n tau plus minus sigma, because this was called n on purpose. So here we go. The equality of this term with this term gives us what we want. So what is it? Square root of 2 alpha prime, alpha n minus, everything except the exponential, and fix n, the sum over n, is 1 over p plus times 1 over 2, sum over p belonging to z, alpha pi, alpha n minus pi, and that's it. The 2 and the p plus are there. The sum over n, and this must be neglected, so we get this. Look, it's sort of a thing that is going to happen most of the time. So when you have alphas and p and n minus p, the sum of the subscripts agrees from the left and from the right. And that's not a coincidence. It's a good thing to happen. So time for a new name. This object will appear so much that we're going to give it a new name. If it would be the quantum theory, we would call it the Virasoro operators, Z operators. These were the Virasoro constraints, and these are called the Virasoro operators. These are still numbers. They will become operators in a couple of days. And they are summed over transverse things. So these are called the L for Virasoro and perp for transverse. The transverse Virasoro operators. It's such an important thing that I should copy it again. 1 over 2 sum over p on z, alpha pi, alpha n minus pi. There we go. One more thing. For n equals 0, n equals 0 is particularly interesting. So what do we get for n equals 0? We get square root of 2 alpha prime, alpha n, alpha 0 minus is equal to 1 over p plus L0 perp. So this equation should also be written 1 over p plus L n perp, because this is a definition. So from here, L0 perp 2, okay. Now, alpha 0 minus is square root of 2 alpha prime p minus. So this is square root of 2 alpha prime p, 2 alpha prime p minus is equal to 1 over p plus L0 perp. So 2p plus p minus is 1 over alpha prime L0 perp. And why is this important? Well, we'll see very soon. But now I think you finally should believe me that we've really solved this. Because the whole idea was that as soon as we have all the alpha minuses, including alpha 0 minus and alpha n minus, we have the whole solution. And here it is, all in terms of the transverse degrees of freedom. So the transverse degrees of freedom determined everything. We've calculated everything. You can now invent in your computer the most general classical string motion. You describe x transverses, put any number for the infinitely many constants from 0 to infinity, and for every transverse direction, and then you calculate the x minuses, and now you have the whole solution. You ask the computer to plot the string evolution. It's done. No constraint, nothing. It's really done. Now, a power of this thing is that you can now calculate the mass of a string. If you have a string doing arbitrary motion, what is the mass of that string? So how is mass defined in a relativistic theory? Mass squared is minus p squared. So it's 2p plus p minus pi, the transverse. So how much is that? Well, from here is 1 over alpha prime, L0 perp, minus pi. Well, I need to look at this L0 perp in more detail. That's 1 over 2 sum over p alpha p I alpha minus pi minus pi. That was for n equals 0. Let's write this out a little more. So it's 1 over alpha prime. Well, the p equals 0 term, let's put it apart. 1 over 2 alpha 0i, alpha 0i. And then there are the terms that have p positive and p negative. And they are the same because they have p and minus p. So you get twice all the sums for p positive. So you get plus the sum over p greater or equal than 1 of alpha pi. And alpha minus p would be alpha pi star. Remember this equation. So we're so far so good, minus pi. And now something good happens. Alpha 0i, this thing is 1/2. Remember, alpha 0i, you need all this knowledge, 2 alpha prime pi. So 2 alpha prime, 2 alpha prime is a 2 alpha prime pi. And with an alpha prime here, and these 2's cancel, and this cancels with that. It's very nice. So the mass of that string is 1 over alpha prime sum over p1 to infinity alpha pi star. It's a number at this moment, alpha pi. Greater or equal than 0. This is one of the first results that came out of Leibniz quantization. In covariant quantization, nobody could prove the mass squared of a classical string was positive. Here you get it. The mass squared is positive and is given by this. You know how it's fluctuating in the transverse direction by these numbers. Put those numbers. This is real because it's things that complex conjugate. The alphas are complex in general. And this is an answer. This is a great answer for a classical theory, but if you think nothing new is going to show up, it's really a disaster of a formula. Why? Because in physics, we really care about massless particles. We want massless photons. We want massless graviton. The standard model is all massless until you put the Higgs and start putting things. So you need massless things. And this thing can only be 0 if all the alphas are 0 and the string is doing something trivial. So there's pretty much no 0 mass squared states of the classical string. The good thing that is going to happen is that in the quantum theory, this formula will be modified. There will be some infinities that arise from normal ordering these operators, and at the end of the day, these infinities will give a shift down in such a way that you can get a lot of massless states. So the quantum theory will save this. But this is the result, and the quantum theory will just add some numbering to it, and we'll do it in the next few lectures. All right, that's it for today.